That's totally fine. So, good to see everybody. This talk is going to be on memory and learning, and there's going to be two of them because there's a lot to cover. So, yep, come on in. So again, this is a good lecture, I think, to go back and thank everybody, y'all, for coming. And want to thank Wikipedia, Robert Sapolsky, and sort of everybody, and YouTube, a whole bunch. I watched videos on YouTube and ask people questions, and they respond. People amazingly respond, and so it's a lecture on learning, and so I figure it's a good time to thank people for learning. And that's where I segue. If you all want to thank me for learning, I would think it would be awesome if you went and made a donation to Wikipedia, because they're asking for it now. I'm a big believer in Wikipedia. Most of this information is coming from Wikipedia from one way or another, or SPCA, or whatever you want. That's my little pitch there. So, all right, this is, I think, going to be cool lectures, because one, we're talking about something real, right? We all have learned things, and we can put our finger on it to some extent. I don't think that any of us have ever said, ouch, my genetics, right? So we can't really think about genetics in that sort of real way, whereas memory and learning is really colloquial. We're really, really, really familiar with this stuff. It's very real. It's something that we all are very familiar with, and so we're no longer nebulously talking about ions. And I think there's a good side and a bad side to that, because there are colloquial terms, and there's a lot of muddying up of this stuff, because I'm going to have to clarify some definitions, and I'm going to probably muddy it up because we just use these terms colloquially often without sort of sticking to an underlying jargon. All right, so there's going to be three parts to this talk. We're going to cover the first two this time, and the next lecture is going to cover the third part of it. So the first part's just going to be the basic sort of stuff that you all learned in med school about memory and sort of categorizing it and retrospective and prospective, all that stuff. The second part's going to be the neuroscience of it. So what do we know about LTP and neurons and all that? And the third part is going to be sort of applying that in a new model of learning to understand things. So when we think about memory and learning, we're really talking about a few things. There's a lot of processes that have to happen. There's sort of the receiving and processing of information, then the memory itself, and then the learning after that. And I'm going to try and define those terms so that we can use them sort of in a meaningful and similar way when we're talking about it. And then I sent in an email about a thinking experiment. And I don't know if you all read my emails, but the idea is that I asked everybody to just sort of think about how come we do what we do. And we're going to do some thought experiments this hour, and we're going to do a whole bunch more the next time we meet. And it has been, and Toral's not here, she is on night flow, but she sent me an email, and in retrospect, it was so obvious. She was like, this sounds just like mindfulness meditation. And I was like, no wonder, I've been feeling so much better about myself. It was so useful for me to actually, take a minute and think about what I was doing and be present and be cognizant of my surroundings and my actions. And it really, it was a good experience for me. And I actually think I learned a lot about myself. And I'm going to try and apply some of that to this lecture. All right. So I got some feedback. And so we're going to take a minute to look about what's going to be the important things to learn from this talk. And so these are not as specific as I would like them to be, but we're actually talking about broad concepts. And so it's going to be an understanding of a few broad concepts. So one thing, I'm going to really focus on understanding memory, consciousness, unconscious, explicit, implicit, retrospective, prospective, and sort of understand what those terms mean and maybe the mechanisms around them. Then we're going to talk about Hebb's law, which is just some basic neuro association stuff. Neurons that fire together wire together. You're going to laugh ultimately when we come back to this in summary, maybe. And then long-term potentiation is going to be the neuroscience part of it. And again, we're going to hammer this in over and over, and it's going to be an important part that we'll go over in summary very briefly at the end. And then the last two are more for the second part of the talk. It's going to be a little bit about talking about how we can apply small concepts to big ideas. And I think that we see this in all parts of science. Tiny, tiny observations, if you realize the scope that they're in, can make for very, very big generalizations of understanding. And I think the last point is self-explanatory.
Can I say something?
Sure.
If you think that Tarek was a little off
Oh.
The same paradigms that we've been using for generations. And this is the kind of thinking that we all need to do. So one of you may come up with something in a new paradigm way to help understand human behavior and pathology that we don't know about because we're stuck.
So to go back, and there's lots of Easter eggs in all of my presentations that really no one ever gets except for me, and I'm okay with that. But since this is on the thought process, I'm going to talk about my thought process a little bit. And I don't know if anyone knows, like, why the heck is he putting this in here, right? Anyone want to take a guess?
Dr. Hobbes.
Dr. Hobbes, right? But how come Dr. Hobbes? Only one other person was privy for this conversation. I asked for feedback, and his feedback was to, summarize what you're going to teach people. And so, again, this idea of why did this come to be this, explaining how did things come to be, so to speak, on a sort of thinking level. And if you pay attention to the slides, there's lots of hidden things in there, and I did it more on purpose in this lecture. That's to keep you all, on your toes. All right. All right, so just another one. Who knows the top caption? I need there's enough of you here. Come on. I can give more hints. Okay. What if I say cats?
It's a cat song.
What's the cat song?
Mr. Mistopheles.
No, it's memory. So, fitting. So, Cats is not my favorite musical, but what I will say is that Andrew Lloyd Webber talked about Cats as sort of being something. Maybe because people gave him a lot of crap for it, but he talked about it as it not having meaning. Like it was just a musical for what it was. And when I hear that, it's sort of a cop-out to me because you can't write music without it having deeper meaning. And because of that, I want to use the song Memory, and it's a perfect example for that. He didn't realize this, but there was a deeper meaning of neuroscience, right? I mean, if you look at the song, it's called Memory, and it's capturing the essence of time and living through time. And, again, a lot of this stuff is going to get cheesy and philosophical, but think about what time would mean without memory. And it's a really vague concept, but if you don't have memory, if you don't have a relation of things to other things, time is a very different entity. Life would be a very, very different entity, and that's what the song is all about, sort of looking at the passage of time and the memories and what that means in relation to our lives. All right. So this is the initial breakdown of stuff, and we're going to go over the prerequisites of a memory in a lot of detail. So the first part is receiving and processing, which is probably the most complicated part of it. This is what we do. This is what it means to be a living, functioning thing. We take in information and we assign higher levels of meaning to it and lower levels of meaning to it. The storage part is actually pretty easy, and I think that we're going to explain that on a decent way neurobiologically, not all of it. But this is what I'm hoping to do in this lecture, and the first and the last one maybe a little bit more next lecture. And then I put reconstructed for a reason. It's not sort of recalling, because memories are not like photographs. They are not factual truths held. They are literally reconstructed every time we recall them, sometimes with great accuracy and sometimes not with great accuracy. And we know this because our memories are fallible to a great extent. And so there's also a lot of data that supports this on a very chemical way. The phenomenon is actually reoccurring to you in the present every time you're re-experiencing it. And you're just putting that placeholder of time in the past. But it is occurring in a very real way in the present as a reconstruction of all of those things that come together to form that memory. And then we'll get into categorizing, which again is in some ways going to be not true to the neurophysiology below it, but is a good way to start. And so, we're going to look at temporal magnitude, temporal direction, and then looking at memory descriptively a little bit. All right, so we'll move on to the next slide. All right, and we'll see how well this works. So the first one is sensory memory, and it lasts about 200 to 500 milliseconds. And this is looked at differently than short-term or long-term memory. And I'm going to talk about different kinds of sensory memory. The one that is really written about in the literature is this sort of very, very brief memory that we have for sensory information that is incredibly detailed. So if you think about it, it's the sort of idea of if you look at a picture or a painting and then close your eyes, for a brief period of time, you can point out thousands of pieces of information that are constructing that. And that is only held for a very, very brief period of time. If you would imagine how long would it take to code that information on a sort of binary level, it would be unfathomable. It's sort of like you're holding that input that was coming in for a very brief period of time. So you're literally not memorizing it. You're almost just, I guess you are memorizing it, but it's probably in a different way. It's probably sensory reconstruction as compared to binary reconstruction, like we might remember a phone number, so to speak.
It just kind of deletes it because it's extra.
Well, we're going to talk about that. And if you think about, we're going to get into that a lot more later, but if you think about, for example, a sound wave, a song, for you to be able to hear a song with a pitch and a timbre, that is obviously getting into sensory memory in a way that's much longer than 200 or 500 milliseconds and probably is similar. And I've never heard people talk about sort of more long-term sensory memory, but clearly if we can hear thousands and thousands of pieces of information in a piece of music that's 3 seconds long. I mean, the vibratos, the timbres, all the different instruments. I mean, if we actually had to code that and write it down sort of on a sheet of music, I mean, there's no way. It's just this sensory information that we have available to us. And then long-term memory is more what we're going to be talking about when we get into long-term potentiation, those sorts of things. So I've got an experiment here, and we'll see how well it works. So I'm not sure. I've never done this before. But it's going to get at the idea of sensory memory. And I've got to give this to you all perfectly. So I'm going to place this down. Actually, I'm just going to make sure I put it the right way. Well, whatever. It's turning around.
Are we betting on this?
All right, let's see. All right, perfect. So what you're going to have on those sheets of paper, and to turn it over, I think if I handed them out correctly, you grab it and turn it this way. Don't turn it yet. So there is going to be either a number 1, 2, or 3 on that piece of paper, or all. Okay? So it's going to be one of those things. Here, you can sort of see it. All right, so don't look at this quite yet. Look at me. Here there's going to be a 1 and 2 and a 3 on the side, and there's going to be letters in rows afterwards. So I'm going to show you a series of letters for just a second. And as soon as I lower this piece of paper, but y'all need pens. Does everybody have a pen? Get your pens ready because this is a very time-sensitive thing, and I'm curious to see how well it works. We'll maybe get lucky. So I'm going to show it to you for a second, and then as soon as I lower the sheet of paper, I want you to turn that over and write down the letters that corresponds to the row of the number that you have. And if it says all, try and write down as many as you can. Okay? So let me know when everybody's ready.
And do we get to know how many?
There's 4 in a row.
So 12 total.
12 total. If Dr. Hobbs gets all, he's going to ruin the experiment. All right, so y'all ready?
So we're looking first there or first
No,
there?
I'm going to lift this up
For how long?
for just a second. Literally, just a second.
We don't know which one.
That's right. So I'm going to lift it up for just a second. As soon as I lower it, turn your paper over and write down the letters in that line. All right, y'all ready?
Yeah.
Are we ready?
Yeah.
Everybody done? I actually probably lifted it up for less time than I probably should have.
We're not supposed to know which number we have.
That's right. All right. So let's turn them over and see how y'all did. So he got the hard one. 2, NSFD. All right, this is a perfect one. That's a beautiful one. 1. Yeah, this guy. You're not allowed to do. So that's very good. That's very good. And then,
I didn't look at the right row.
okay.
I was looking.
Okay. So, wow, all right. Perfect. All right, so this is perfect. So look at what actually we saw here. This is not going to make any sense on the video. But the idea was that you all were amazingly actually able to get the 4 in your row, right? So, but if you had to guess more than that, it was lost. But the magic to this experiment is you didn't know which one. So you couldn't have learned them all. You had all of that information only for long enough to record about 4 of them. But for that brief period of time, you knew them all. And if you think about that, you encoded 12 pieces of information. I mean, instantly, a snapshot, you held 12 pieces of information. But you only held it for a brief period of time. As soon as that information was gone, you could only get out 4 pieces of information before it was gone. But for that brief period of time, you held all 12. And that wouldn't, had that not been the case, you would not have been able to guess which ones. Does that make any sense?
Or maybe another way to look on it is, we got the picture. It was a picture.
It was a
12
picture.
letters.
That's right.
And then, once you realize what your row is, you're trying to figure out, zoom in on that part of the picture.
That's right, and that's probably more true. So you stored it as sensory information, and that's what we're getting at. It was not yet converted into working memory. Well, it's going to get complicated when we start talking about these things, but it was not yet stored as digital information. And I'm going to talk about digital and analog as if that's like real things. I make these terms up because it makes sense to me, and we'll talk about them more later. But if you think about it, you stored not just 12 pieces of information. I mean, you stored 1,000 pieces of information, the relative distance of each of those things to each other, the color of them, the shapes of the lines. So that, it would be impossible to store that in a binary form with that level of accuracy. So it's clearly a different mechanism that's storing that than would be storing, say, if you had to sit down and memorize all those things.
But I imagine it'd be easier for us to do this unless if they were Cyrillic letters.
Absolutely.
And,
And-
or like picture, because I don't know Cyrillic letters. Or Japanese characters, even though
And-
it's not any more complicated visually.
Japanese characters and Chinese characters is going to be like the big punchline of next month's talk, which is, it's interesting. It sort of like dawned on me, but we'll get there, and I think it'll hold some value. All right, so this is about temporal direction. And so when I'm talking about temporal direction and prospective memory and all that, I've got to bring up HM. And most of y'all have heard of HM. He's the guy who had his bilateral hippocampi blasted, and he could no longer form prospective memories. And so he still had working memory, he still had some of his old memories, but he could no longer form prospective memories. So likely a part of forming current memories is occurring in the hippocampus, and that's my neuroanatomy for this. We're going to do a lot more neuroanatomy later. But again, just generally, prospective memory is the memory that we're going to be learning in the future. Retrospective memory is memory that we have learned in the past. And working memory is really the awesome part of all of this. And so we've got the past and the future, and so where do you imagine working memory happens? Now, in the present, right? And so working memory is really where we live. That is everything that we know to some extent is happening in working memory. And it is pulling on information from our whole life. And nothing that we're aware of happens outside of working memory. Maybe, I'm guessing that's probably true. And again, here's another thought experiment. So we're going to take a walk through my mind and sort of see how we got to get here. Do you want to imagine why the hell this picture is on this slide?
It's not me again.
No, it's too cute. So I did a search for present because working memory happens in the present. And then this one popped up early on, and I was like, I love this. Does anybody know who this is?
Stitch.
It's Stitch. Okay. Has anybody seen Lilo and Stitch? Oh, this is unfortunate. Has anybody here seen it? All right, that's the homework assignment for next week. So I'm going to give you a 30-second synopsis of Lilo and Stitch. So Stitch is an interstellar creature that was genetically made to be the most fearsome warrior killer in the universe. Okay? He ends up crash landing on an island in Hawaii and gets befriended by this young girl, Lilo. She's this little Hawaiian girl who has got some problems of her own. Has some difficult living situations, social services are involved. It's an awesome story. And it provides a very great opportunity. And Disney is amazing at what they do. And so think about it. This is the perfect nature-nurture argument. You have this creature who is genetically created to be the ultimate killing machine, and it lands with a young, caring little girl who, and the entire premise of most of the movie is, what is Stitch learning from Lilo? It's a complete movie about learning. And it's perfectly showing how genes and environment can interact to produce very varied things. And you can imagine, were Stitch not to have that experience, he would have ended up somewhere else. And so ultimately the guy is sent back to sort of destroy Earth and destroy Stitch. And we're going to watch a little video here. This is near the end of the movie, but it shouldn't spoil anything. Hopefully it loads. So again, I think that's a great showing of resilience. So, this guy is looking at him as, a product of his genes. You're vile, you're foul, also cute and fluffy. And so that's something that, Lilo told him. And so I think it's just a wonderful model. And this is where I give my, again, little aside on how I think we're so lucky to be psychiatrists, because our work and play tie together so well. And so, we get to view this from a completely different perspective than other people. And it also helps us, I think, every book we read, every song we hear allows us to relate to people in a certain way. And I know that the people that I've worked with give me completely different perspectives when I see things happen in life. And so, again, I think that we're just very lucky to be given the opportunity to really get privy to information that is very personal and very meaningful. So the other thing that I wanted to mention, I've noticed this about me, is that there's a lot of magic that sort of happens, I think, in the room with you and a patient. And it's sort of like E.T. Or Green Mile, where we really sort of can take people's pain. And I've noticed that with me. And so take care of yourselves when you're with patients, because it can be really easy to absorb people's problems, and it can weigh on you. And I'm not sure if we can even be fully empathic without that happening a little. I'm not sure, but I certainly know that when I'm with a patient and they put things on me, they feel better, and sometimes I have a harder time. But that's okay. That's what we do. All right, some more categorizing. So this picture is obviously cut in half. We're going to cover the other half on the next side of the lecture. For this side of the lecture, we're going to be thinking about typical sort of learning, learning in the individual. And so we'll start at the top with explicit learning. This is sort of what we think of with our everyday facts, right? So the semantic learning is just a fact. And so, right, a foot is 12 inches long, that sort of thing. Autobiographical and episodic memory really are probably two of the same things. They parse them out here. Autobiographical memory includes sort of the times, the feelings, the location of stuff that happened to you. Episodic is the times, place, all that happened to someone that's not you, but people would argue that sort of it still was you who was experiencing that. So it's probably sort of the same thing, it's just different ways of looking at it. But one thing that I will get at is that it's clearly not this chopped up and dry, and we sort of know that because where did I write here? Did I even write something here? Oh, I didn't. But let's say I said 3,000 people died on the 9/11 attacks, right? That's semantic memory, but we can't know that fact and have it separated out from everything else that we are thinking about 9/11 and death and emotions and where that takes us and what that links to. And so these are obviously just categorizations for the sake of being able to think about things differently. The big differentiation between explicit and implicit is in whether it's conscious or not. So explicit information is information that is made conscious. Implicit information is information that is unconscious. And so procedural would be your standard riding a bike or juggling or something like that. One thing that I've never heard people get into is, what about sort of the non-learned in the traditional sense procedural stuff? And that would be like digestion or breathing or these things that we can do at birth, but were never really learned. And I think that that's going to swing a little bit onto the other side of this, but it's really going to also be talking about learning is a very nebulous concept, and it can happen in a lot of different ways. And I talk a little bit about intragenerational, meaning learning that happens within your lifetime, and intergenerational, meaning learning that happens across lifespans, learning that happens in the genes. And Dr. Rob is giving me a no-no, but I think that clearly insects are born knowing things. They probably don't know it in the same sort of way that it's acquired from us, but they can respond to their environments in certain learned ways that was passed on in a genetic manner. And we'll cover more of that next time.
I'm just going to chime in one thing. Remember, Turk's talking about unconscious. He's not talking about the Freudian unconscious. It's a completely different ball of wax.
So priming is an awesome, awesome concept, and it's something that I think offers us power to help people. And so what priming is that information that is given to us can influence us in the future without us being unconscious of it, without us being conscious of it. So let's say they do this experiment where they take a whole bunch of words and they just have people view these words. And there's 3 groups. There's a group that views generally rude words, words that are associated with rudeness, words that are neutral, and then words that are associated with politeness. And then afterwards, they just talk to the person. And the people who viewed the rude words were more likely to interrupt the interviewer than people in the neutral group, and the neutral group was more so than people in the polite group. The more interesting, I think, experiment that they did was simply have an interview with people, a standard interview, where the interviewer handed the person a drink. And in one of those situations, they handed them a warm drink, and in one situation, they handed them a cold drink. And following the interview, they had these people fill out these forms with a lot of stuff. Some of them was, how much did you like the interviewer? And use words to describe the interviewer. And it's sort of fascinating how something as little as that influenced how people viewed the interviewer. And people would literally write, who were given the ice cold drink, she was ice cold. I mean, it's fascinating when we sort of see what goes into the way that we perceive the environment. And we're going to talk about this a lot, modules being used redundantly, and we're going to talk about some of this. I hope I got it in this lecture about how we use a lot of primitive types of things to explain way more complicated types of things. Oh, and the other thing that I didn't mention here is the difference between recall versus recognition memory. And recognition memory is simply, I've seen this before, whereas recall memory is, it's sort of like a multiple choice test, whereas recall memory is a fill-in-the-blank test. And clearly there's a huge difference, and I think that we are taught in some ways to learn recognition, whereas that is not very useful information. Really, if you can't access it, it doesn't do you a whole bunch of good. A patient doesn't come in and say, well, should you give me this A or this B or this C? It's sort of, you have to generate this information on your own. All right. So here is a model for working memory. And it's an old model. It's been updated. We're going to talk a lot about working memory because I think it's a very important concept in the formation of memories and learning. But I'll just briefly go over this. So the central executive is sort of the boss master. It's going to include stuff like attention and what to focus on. The phonological loop is described as, if I say a phone number, you keep repeating it, and as long as you keep repeating it, you can hold on to it. And it's sort of to help with retention of auditory information. The visuospatial sketchpad is broken into 2 parts. The visuo sketchpad, which says, this is what the object looks like, this is its color, this is its texture, this is its size, and then the spatial sketchpad, which organizes things in a spatial way as far as location goes. So, I look at all of you, I've got, the space holders for each of you, and then the visual cues telling me it's you sitting in that seat. So it's those 2 things that come together. They're probably very different neural circuits. Spatially, we think of the hippocampus and stuff like that. Visual is probably more higher order association stuff. And then the episodic buffer got added later. And it's really probably important for sort of determining what is and what is not going to be held in this working memory. So we've got tons of information coming in. We have to decide to some extent what is relevant in the immediate sense, what can we use to make this stuff up. It's sort of like determines the day's residue, as to use Freud terms, of what can go on into a thought or a memory. And so there's a lot more complicated theories that people have added to this, and I'll put a spin on them So people talk about, long-term working memory, which is the idea of clearly we can have working memory for more than just a few seconds because, you couldn't read my paper if you couldn't. Because when I'm referencing a point from the paragraph behind, you have to be able to access that. And likely what's happening is that if you can organize that information into a single chunk of information or a couple of chunks of understanding, when you need to recall it, you don't have to recall the whole paragraph. You're just recalling those functional pieces of information. And that's, a good thing to think about when you're reading something that's complicated. If you can't understand it, they're probably referencing something far back that you were not able to digest into a workable piece of information to recall later. And, it's a way to think about when you're going forward learning stuff. If you really can understand things, you're going to understand them sort of in a simpler way. And then they get into the time-based resource sharing model, which I think holds a lot of validity for explaining how we think. And the idea is that we have a certain amount of horsepower or, processor speed or whatever. And that's going to differ among all of us. And within that processing speed, we have to do a lot of different activities. And so there's two main things fighting for the resources. So one thing is processing. So performing operations with sort of objects in our working memory. And the other is maintenance of those objects in our memory. So if we want to hold, say, three numbers in our memory and then perform math on them, the more complicated the math, the less we are able to maintain those three numbers. And they've done a lot of experiments to show this. And I think if we just think about it, we sort of know that. The more the demand of the operation, the less we're able to hold into our mind at a single time. And so we'll come back to this model a little bit when we're thinking about sort of illness expression. The next one was interference theory, which gets into the idea of what do they call them? Proximity errors and transposition errors. And looking at, if you were to look at some of your things that you had written down, I saw on that B, somebody wrote an F instead of a B. And you can imagine why you would have a transposition error of an F instead of a B. Because when you're recalling that sensory image, it's not perfect, and a B is more likely to look like an F. And that's all that that's getting at, is that, and the other thing is, let's say, well, I'll go to the board quickly. The next one is a transposition error, and I think we've all done this as well. So if you have like a, if you had that versus you were more likely to flip these spatially if you had to recall a list than these two. And so you may flip other numbers, but the more similar two pieces of data are, the more similarly coded they are, and so the more easy it is to mix them up. And if you just ask people to remember strings of things, you'll clearly see those two numbers are going to get flipped a lot more commonly than the bottom two numbers. And so it's just getting at trying to understand how we can hold on to sensory data by doing some experiments. All right. So, and then people try and think about, how do we store multiple pieces of data? How does this stuff happen? And nobody really knows exactly, but some people have some good ideas. And so let's say you want to remember, say, red square and green triangle. All right, so it's the idea of binding concepts together to make a coherent image. We want to remember that there's a red square and a green triangle. What people might say is that, well, the symbol for red will fire, temporally connected at the same time with square, and then there'd be a pause, and green would fire at the same time as triangle. And so that is how we connect pieces of information in our brain, because there is not a neuron for green triangle, because we could not code for every single piece of information if we had to code it one-to-one. So the idea is we can take smaller pieces of information and by correlating them somehow across the brain, create much more complicated concepts. And then to get into the idea of the central executive and attention, they look a lot about what is attention. And so people talk about the top-down versus the bottom-up models, and that sort of gets at a little bit reductionistic, but I think it's useful at this point. So top-down is we have this model that's looking at sort of cognition, higher levels of functioning, delayed gratification, and the bottom-up up is sort of the sensory side. And you can imagine that these two things are fighting each other for control of attention. And it's similar to lots of things that we're going to see repeated over and over. There are different modules in the brain that fight for attention. So this tries to inhibit this, and that's how it gets to win, and the other one would try and inhibit, the subsequent one. So they sort of vie for supremacy. And so if you want to take a step back and think about that when we're trying to make decisions, we can almost say this sometimes, like we've got an angel and a devil on our shoulders, and we feel this internal turmoil as far as pulling us one way or another. And so I want to just bring that up, the idea of ADHD, right? So attention deficit hyperactivity disorder. And I'll be brief because this isn't about ADHD, but firstly, I think it's completely a misnomer, right? Attention deficit. These people do not have an attention deficit. They have a difficulty with the environment that they're in based on the way that they process information. So if you think about that, if you have somebody, and you can imagine lots of ways to get into this trouble. So you've got this resource model where you've got, a certain amount that has to go into maintenance, a certain amount that has to go into processing, but also we have to decide what information is going to be in here. If you value sensory saliency more than cognition, it's not that you have a deficit of attention, it's that your attention is focused on other things. So, you all are focusing on me, you're focusing on this PowerPoint, you're not focusing on the whirring of the projector. So that sensoriness has been pushed down because it's not useful. If you are unable to filter out the non-saliency of that sensory information, you can have all the attention in the world, and you're going to be able to tell us all about that whirring, but you're going to be diagnosed with ADHD. So it's a difficulty with filtering out what is novel attention versus what is useful attention, and having control over that. And so that's just a quick aside. And you can imagine that if you don't have a lot of processing power, or you don't have the ability to filter this stuff, you could express sort of difficulties with learning in a sort of structured environment. All right, so now onto the neuroscience part of the talk. So this will go quickly. This is just a picture that I had shown before, and this is where integration has become really, really cool, right? So now we can begin to think of all of these things, and you're going to need to think about all of these things to understand these concepts. So we've got the neuron, we've got the synapse. This is where a lot of the action is going to be happening. And so when we talk about LTP, all that means is that two neurons are going to interact in some way so that over time their interaction changes in a persistent way. And that can be in a qualitative way, it can be in a quantitative way. It can either be that this has to fire more to trigger an action potential here, it has to fire less to trigger an action potential here. If it fires an action potential, it does something different on this one than it had before. But all that this memory learning LTP business is sort of getting at is that we can change the way that our neurons interact if certain things happen. And there's going to be lots of different mechanisms for that. It can be sort of the epigenetic side of it. It can be on the neurotransmitter side of it. It can be on a receptor side of it. We're going to focus on a specific type. But before we do that, we're going to talk about Hebb. And so Hebb is pretty much like a god of neuroscience. And so I want you all to remember this. All right, so say it with me. Neurons that fire together, wire together. Neurons that fire together, wire together. Neurons that, I'm going to keep going until this guy, they're done. All right, neurons that fire together, wire together. That's a really important concept, and we're going to go over that in more detail right here. And so if you can know these four things, you'll get the basics of this long-term potentiation business. So the first one is that there's a certain amount of stimulation that has to happen for long-term potentiation to happen. Every time an action potential fires, you do not get long-term potentiation. It requires repeated action potential, one after the other, on the order of about 100 hertz, so 100 in a second. And I'm going to show you why that is on a sort of very nuts and bolts level. That threshold can change based on different things. And again, we're talking about, his threshold might be lower than mine, etc. And we can already start to see why some of us might learn differently than others. And then input specificity is the other big one. So we're going to have to sort of state neurons that fire together, wire together. It's sort of like synapses on a neuron that fire together enough, wire together with their respective dendrites, and we'll sort of show that in more detail. And then associativity and cooperativity are just getting at the idea that if a whole bunch of dendrites come in, synapses come in on dendrites, just so long as tetanic stimulation happens, all of the dendrites that are firing get long-term potentiated regardless of how much they contributed to that action potential tetanus. And so I'll draw it to make it obvious because those words don't make a whole bunch of sense. And so we'll just draw it, and hopefully that will make sense. And I'll take this with me so I don't mess it up. All right, so this is actually, I think, going to be pretty cool because it's the first time we're really going to be able to combine all these concepts, and it's going to be like a semi-eureka moment. At least it was for me. So, all right. We've got a few. So these are neurons, okay, and they've got their own dendrites, and then all right. All right, so you can see we've got 3 different neurons, presynaptic neurons, synapsing on 2 postsynaptic neurons. And so we're going to go through each of these things. So FA, for example, and we can name these like I did sort of before, but like, you know, AD1 and AE1, and so that we can talk about them. So if A fires enough, let's say A fires 1 action potential on D, nothing happens. If A fires enough action potentials on D to cause LTP to happen, this gets potentiated. This and only this. This does not get potentiated because not enough stimuli happened here to set this off. All right, so that's one example just to show the basics of tetanus. One won't do it. It has to be a train of them. All right, the next example. AE1, A fires and AE1 fires on E and a couple action potentials goes off. B fires and it fires off on BE1 and a couple action potentials go off. But neither of them firing alone causes any LTP. If A and B fire at the same time, the summation of these two cause enough action potentials to happen. Do y'all want to guess which synapses get potentiated? A1 and BE1. Right? So both of these were contributing to the summation of this. So these two and only these two. This doesn't get it, this doesn't get it, and this doesn't get it. So let's say we do this again, and A and B fire, and they are enough to set this off, but then C happens to fire at the same time, right? Even though it wasn't really necessary, it also gets potentiated, just so long as it happened at the same time. So it doesn't matter how much each one is contributing to the relative stimulus. It's just that each one that is firing at the time that the tetanus train is going on is going to undergo LTP. And that sets up a little bit of a dilemma when we're actually talking about how does this happen on a neurobiological basis, right? Because the whole point of my talks is trying to make like a nuts and bolts physical sense of this.
So it's like Facebook.
Yeah, it's sort of like Facebook.
You say friending people, and then you get friends of friends. And you get LTE friends. Yes.
That is awesome. Yes, I hadn't thought about it that way, but I like the analogy. So, all right, y'all down with LTP? So we break LTP into early LTP and late LTP. And early LTP is protein synthesis independent, which means that no DNA business has to happen. Late LTP requires protein synthesis. All right, so this can happen in lots of different models. The most common one that's studied is the NMDA glutamate one. So that's what I'm going to talk about. Again, remember, 90% of the excitatory neurons in our brain are glutamatergic. Okay, so we talk about serotonin, we talk about dopamine. When we're thinking about the brain, the mass of the brain is glutamate. And so I think that you know, it's really important to sort of understand that this can have a lot of effects on the brain and on behavior. All right, so I've got to give a shout out to Neurodemystifier on YouTube because he had this excellent, excellent video that really helped me understand this in a very practical way. And so I'm going to use some of his ideas and expand on them a little bit. All right, so here we go. Let's see how well we can do this. Dun, 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 dun. See how much I need my cues. I shouldn't, but just in case I forget, I'm going to keep it here. All right. All right, so we're going to start at the very top. Okay. All right. What's this? A light bulb, right? So this is our idea or our memory, okay? So this is our first module. This is something we can all understand, and it's all happened to us, okay? So we can call this a simple behavior or a neural module. All right. So we're going to go to the next level of organization. And I can't draw at all, but what's that?
Brain.
A brain, yeah, okay. So this is going to get to the neuroanatomy. And this is what we're going to cover in 2 weeks. But imagine this is sort of the hippocampus, because it's where it's mainly studied. Okay, and then we can go to this level, right, which is the level of the neuron. All right, and so we're back into our realm of neurons here and understanding what that stuff means, right? So neurons, ions, receptors, neurotransmitters. And you all can really begin to sort of see what we're doing here. Next, we're going to focus on right here. And, All right, so here we go. We got our synapse. Okay, and here's our vesicles in our synapse. And then we've got this here. All right. Hopefully I have, they're going to kill me on colors here. All right, that one works, and this one works. All right, so we've got 2 different kinds of receptors here. All right, so we've got NMDA receptors, and we've got AMPA receptors. All right, let's see. So now we're going to zoom in here, all right, on these receptors because they're super, super cool. All right, and so we've got, let me come back to this silly color. Oh, I put the wrong cap on this one. It leaves a lot of confidence in my teaching ability.
That was non-associative.
Yeah, there we go. If I had more colors, this would be prettier, but I don't. So, there's a point to this. I'm sorry that it's taking me so long to draw this. Okay, so we've got our zoom in on our receptors here. All right, so here's our AMPA receptors. It's actually a 4 subunit thing. I'm only drawing 2. But these are glutamate receptors. All of them are glutamate, okay? And when glutamate comes in initially, it binds here, and like we remembered before, we get that conformational change. So these are actually together, and then we get the conformational change, and they pull apart. And all of a sudden, we're allowed to have ions come through. So glutamate binds, and then sodium ions come in, right, and create a lot of positive charge, okay? And so that fires action potentials. This here actually requires 2 different things, glutamate and glycine, but that's not a huge deal. But the more important thing here is the magnesium blockade. That does not allow ions to come through, regardless of whether this is stimulated or not. And just so we all can be familiar here, do you all have any idea what this green thing is that these receptors are sitting in? It's a membrane. And what did I keep saying that membrane's made out of? Phospholipid bilayer. So you see these things here? You remember those things that I drew last week? So again, we can begin to see inside of here where I want to. I could draw this, draw it down, and remember it would be that multiple, this business sort of thing. And so we can again begin to see levels of scale here. So we can already begin to imagine that these are fatty molecules and these are proteins, and we're on that sort of level. We can zoom in and out through all of this sort of thing. But anyways, so all of our action potential chains come in. And once it gets enough positive here, we can expel this magnesium. Okay? This opens up this channel, and that's why it's called the coincidence detector, because this is what determines action potentials. This is what determines LTP. If there's enough of this positive summation charge, positive repels positive, this opens up, and all of a sudden we can allow in sodium and calcium. which is the one that's going to be very, very important, right? So as calcium concentrations go up, it activates something called CAMK2, okay, which is calmodulin dependent or mediated kinase. And this is super important. So now we're going to come back to here. Okay, so NMDA AMPA. I've got to remember my colors here. All right. So there are endosomes here that have lots of these receptors already pre-made. A lot of these AMPA receptors already pre-made. And then CAMK2 does a few things, a few very cool things. So it's a kinase, so it adds a phosphate group that ultimately kicks this up into the membrane. So it's stored here, it goes in, and it causes this endosome to go to the membrane. And so now we've got more receptors. It also goes in and adds a phosphate to the AMPA receptors, which make them more efficient. So you can already see here, this relationship between these two has changed. The cool thing about CAMK2, so we're going to talk a few things here. So firstly, it has a low affinity for calcium. There's another molecule called calcineurin, which has a high affinity for calcium. And so you can already begin to see that we're in this battle for things, because calcineurin does sort of the opposite. It pulls these things back into endosomes. So you can see here calcium is the modulator of these things to some extent. The cool thing about CAMK2 is that it can autophosphorylate itself. And we're going to talk about this concept later, because that is where ultimately the long-term part of long-term potentiation is going to come from. So we're going to talk about the autopotentiation of these molecules, because it ultimately is getting at, I think, like the coolest concept that I've maybe even come across in neuroscience. So let's talk through this very quickly. Okay, we have an idea. It's somewhere in the brain. It's a neuron. We're understanding all these things. We're understanding the receptors. They can come from genes, right? Mine might be different than yours. There could be epigenetic changes. All of these things are going on with ions. We've got to understand the physics and all that. Blah, 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 blah. So we've got a neuron. We've got a synapse. Action potentials happen. We're going down here. First, the glutamate opens up. Sodium comes in. Action potentials go off. If there's enough of a positive summation, you kick out the magnesium from the NMDA receptor. It opens up. Sodium and calcium can come in. Calcium increases and activates CAMK2. CAMK2 then adds phosphate groups to put AMPA receptors into the membrane and increases the efficiency of AMPA receptors. All right. So I think this is a really important concept, and it captures a lot of things. It captures a module very, very beautifully. So I want you to close your eyes, and I'm going to talk you through it and imagine these pictures. If you need to, open up your eyes and re-get the pictures in. All right, we've got our light bulb module zooming in on the brain and the hippocampus, zooming into those beautiful neurons that you all know and love so well, zooming into the synapse where we get the glutamate. It's binding to the AMPA receptor, which is opening up, bringing in sodium, causing action potentials. When enough action potentials happen, the NMDA receptor expels the magnesium plug. Calcium can then come in. Calcium can then bind CAMK2, and CAMK2 can put the AMPA receptors into the membrane. All right, so while I'm erasing this stuff and getting it ready for the next one, you close your eyes and really try and imagine what's happening here on your own. And I assure you that we'll have some stickiness to it come a week from now when we'll need to use it. Okay, you can open up your eyes so you don't fall asleep on me. All right. So again, this is going to be getting at, I'm going to say the same things a whole bunch when I think they're important. The right time for the right amount process. If you remember back to inflammation, and we talked about glutamate being upregulated in stress and inflammation, we could imagine how that could help the cascade of learning, but also on the flip side, excessive glutamate can cause bad things. And just to repeat the same sort of things over and over. This is the slide to show the connection between the early phase and the late phase of LTP. Pretty much what we had been seeing up here are glutamate receptors can go in, activate this stuff. This is where the connection is going to happen in this cascade of what they call ERK or extracellular signal-related kinases. It's part of a MAPK family. These things just come up if you read about them. they can trigger other stuff that ultimately can lead to gene transcription and LTP expression. So if we look here, this is how the most common model of thinking about how late LTP works. So if you think about it, we've got to maintain Hebb's rules of input specificity, associativity, etc. But this is a genetic phenomenon. So what happens is that these things can activate a transcription factor, which is ultimately going to go down to the nucleus, and it's going to create so this is normal part for the course. Goes in there, transcription happens, it creates mRNA. That mRNA then goes to the cytoplasm. That's, again, always normal. This is where it's different. It does not get transcribed in the cytoplasm. It gets picked up by a motor protein and taken back into the dendrites. So the thought is that every single place where a signal had come in releases this synaptic tag, and it hasn't been identified yet perfectly, and only the synapses, or the dendrites that had a synaptic tag can grab this mRNA molecule and pull it off the transporter. And it actually creates these proteins at the dendrite. So if you look at it under sort of staining, these things magically appear in the dendrite. And so that's very cool. I mean, that's like, I'm sure that there are other things that do that too, but that's the thought between how this happens. So, when you create mRNA or you create a protein, it should change the whole neuron, but this is a very fancy way of, it goes back to all the dendrites, and only the ones who have this tag can grab the molecule and pull it in. And often what it's doing is it's creating more AMPA receptors and other types of things that are necessary to maintain a strong connection at that synapse. All right. Oh yeah, the other big important protein is PKM zeta. I'm not going to talk a whole bunch about it, but it's similar to the KMK2 equivalent. There's a lot of cool data that if you actually block PKM zeta, it's thought that it's required for the maintenance of memories. So you can erase retrospective memories for a while back in a rat by giving them an inhibitor of this. And it again goes on to the idea that we are constantly maintaining our memories through this cellular mechanism. And so, again, there has to be a feedback between LTP or long-term potentiation and long-term depression, or else there either be only these synapses and then the other synapses would go away. And so there's lots of models of how that happens, probably changing of threshold levels in these interactions between, KMK2 and calcineurin, etc. But let's see, whatever. That's not that important. Let's move to here. All right. So I'm going to talk a little bit about what realization that I sort of had that was very helpful for me. Well, first of all, I'll just give the broad summary. We learned about memory, categorizing it, implicit, explicit, priming, procedural, semantic, all that business. We learned about Hebb's law, which was neurons that fire. I hate you, Peter. Neurons that fire together, wire together. And then we learned about LTP, and you all can close your eyes on your drive home and imagine it as you're swerving through traffic. So, all right. So, the cool thing, I think, about KMK2 and PKM zeta is that they act differently than other molecules that I've ever seen. And so, if you can imagine what this means on a molecular level, that we have some experience, whatever it may be. We read something, we hear a piece of music. That has a neurological correlate. It sends action potentials across certain neurons. That signal leads to a change in a protein. That protein then can recreate that signal pattern in the brain. So it's sort of like you can have the output without the input. And think about that. Your neuron continues to live as if, to some extent, that input is still coming in. And that was one of the most mind-blowing things to me in all of this neurobiology business. And if you think about it, of course that has to happen, because we are living a lifetime of memories. And I will come back to that in a minute. Does anybody know who this is? It's Stephen Wilshire. He has a ridiculous memory. He will be taken up in a helicopter, flown around a city for like 30 minutes. Then he'll come back and over the next few weeks draw the city like perfectly. He gets like the number of windows in skyscrapers correctly. So there's a lot of variation in memory. I didn't talk about illness of memory. I didn't talk about mental retardation. I didn't talk about any of these illness syndromes. Understand there's a wide spectrum. Like most things, there's going to be things on either end. And in the middle, there's our normal individual variation. We have these genes for these things. We have SNPs for them. We have epigenetic changes for them. All right. So now we're going to go back to this idea of CAMK2 and PKM zeta and what that can really mean to us. So every single experience that we've had that's resulted in this LTP, so everything that's been significant in some way or another lives on in the present with us. So when we are in our working memory and we see something, we are pulling on a lifetime of experiences to understand that. When we speak the language we speak, we are pulling on years of growing up with that language and hearing it and seeing what it meant. And that is happening so easily to us that it's hard to fathom. But if you think about how complicated it is to create a sentence with its symbols, we are living with a lifetime of this experience and learning. And so, I wrote the really cheesy paragraph in the handout of, it seems silly, but in this chemical, in this synapse, in this process, it ultimately determines, what language we speak and whether we say tomato or tomato. It determines the football teams we hate and the people we love. It determines, what music we like, what songs we sing, can we ride a bike. It is our aspirations, it's our dreams, it's our love, and it's all this accumulation over time of tiny bits of information that can integrate and grow and create more and more sort of beautiful and complicated concepts. And so now I'm going to go on to a little bit of hubris here. So animals have known almost forever that their offspring look like them. So dogs can tell who their kids are. Human beings probably since the beginning of time had a general sense that our kids look more like us than our not kids. Certainly more recently, we know that, our kids share similar traits as we do. The idea of a gene came up way before we found DNA. That's a very, very simple, easy concept. We all know it. It's common sense. But it took somebody like Darwin to realize the power in the ability to pass on traits and the ability for what that quanta, the quanta of the single individual transmission of traits, can ultimately express. So from this single idea of you can pass on information, he wrote The Origin of the Species. So everybody knew this information, but he was able to take it and then apply it broadly to show the explanatory power that it has. And so this is where the hubris connection comes in. I think that, and I'm going to make an entire hour-long argument next week, and it's going to have nothing to do with science, that if you think about where we come from, we are learning. That LTP process is the quanta of everything we know. And it's hard to imagine that a memory, a thought, an emotion is a chemical, but think back to Darwin and evolution and realize how powerful the accumulation of tiny, tiny things in a concerted effort can be to create very, very, very complicated systems. And I'm going to very, very much do my best to convince you of that. So I guess with that being said, I appreciate all of your attendance. And hopefully that's a little bit of teaser to get you all here next week. And I'll take any questions if you have them. All right. I'll turn off the camera and then take questions.